Okay, welcome back, everybody. Hope you've had a great afternoon so far. This session up here is a 2-hour tutorial. You've got, so just letting you know that the session down in the main hall is scheduled to be a longer one. So like when we break from here, you might not find some people outside, and you probably shouldn't go traipsing through the main hall just because they might still be underway. So with that said, it gives me great pleasure to introduce Adam Green, and Adam will be giving us a tutorial in distributed computation in Python in a bunch of technologies that I've actually, I've heard of those ones, but there's a couple in here that I've never heard of, and I can't wait to hear about them. So let's make him feel welcome.
Hello, everyone. Thank you, everyone, for coming. I really didn't think this many people would show up, so yeah, thank you for your time. So the notes for today, the materials for today are in this repo here. I appreciate because of the Wi-Fi here, it might be a little bit difficult to clone that. You can't use SSH, which most developers do. And also the Wi-Fi here apparently isn't great. So yeah, if you can clone this, you'll be able to run the notebooks. The sessions are based around 3 separate notebooks. The first one is kind of an introductory warm-up session about functional programming. The reason we introduced this in a course about distributed computation is because a lot of distributed computation leans heavily on functional programming concepts, map in particular. So the real important thing about this section is you know how to run a map in Python. That's kind of the big thing. So yeah, 20 minutes of kind of theory of me talking, and then 20 minutes of you guys having a chance to have a go at some exercises, which is obviously conditional on being able to clone the code. The second notebook, single machine, this is all about distributing computation on one machine. We'll only use the Python standard library there, so everything should hopefully run pretty easily. There's no clusters or anything kind of to set up. And in that section, we're talking about solving 2 types of problems, IO-bound problems and CPU-bound problems. 2 solutions for those, Async IO and multiprocessing. Also go into a bit of like what threads and processes are, CPU cores and stuff. This is an introductory focused course, and what I mean by that is that what I'm trying to do is bring everyone along for the journey. So some things might seem a bit basic, but hopefully, once we get going, we can end up in an interesting place. And then the final notebook, which is running on many machines, which is kind of the inverse of the second notebook. This is a whole bunch of external accounts. I think 2 or 3 external accounts, especially if you include AWS. A bunch of different random packages that people won't have heard from. So that's kind of the exact opposite of the second notebook. And I'll be giving a demonstration of running a Dask cluster in the cloud using Coiled and Prefect as well. Don't know whether you guys will be able to get that running yourself because you have to sign up for this account and that account and all these kind of things, but I'll be here to kind of give you guys a hand if you want to. This third notebook, you can read it in Binder if you want to. This here is an example of the notebook running in Binder. This third notebook, you won't be able to run in Binder because I don't install Dask onto Binder because Dask doesn't like, Binder doesn't really like Dask or Conda in particular. And so you can see there's kind of 2 requirements files in here, Coiled and requirements.txt. That's because we're targeting 2 different environments here, the Coiled EC2 environment, which is in notebook 3, and the Binder environment if you just want to run notebooks 1 and 2 on those on Binder. Cool. This console is not returned, which is interesting. Anyway, so we can start it with the first section. Does anyone have any questions, or did everyone kind of get a Sorry? Sorry, what was that?
We cannot find that link to see it.
You can't find the link.
Where is it?
Oh, it's on GitHub, right? If you go to, I would just copy and paste this in Google, right? But is there a way for me to share text with people here? No, there's no Slack channel or anything. Okay. So the way that I would find this, I would look for my own GitHub profile, ADG efficiency. GitHub. And of course it will come up for me because I'm me. And yeah, hopefully be able to find some of the other random stuff I've done on GitHub. Then go to my profile, and then repos, and it'll be the top one. Does anyone want me to go over that again? Sorry?
Maybe just zoom in on the URL.
Ah, yeah, sure.
Yeah, paste it into something in big text.
Okay. And, right, sorry, I need to do something. I can't use Jupyter Lab without Vim bindings, unfortunately. Where were we? Okay, link is here. And I'll kind of let you guys take a second to get that working. I'll split this here. I'll suggest, can everyone see that okay? Hopefully. These 3 vertical bars are interesting. I'm just going to get going. If anyone has any problems, what I suggest is we'll take a break after this notebook. You know, when we did the practical session, just come up and I'll give you a hand, you know, running through your machine and stuff. Cool. So first section on functional programming. So outcomes of the course, this notebook. This is the big one, right? So as long as you know what a map is and you're comfortable with a map and you can do maps, we're kind of all good. The genesis of this course is another course I gave in 2020, March 2020, before the world ended. And in that course, which was a lot longer, we covered MapReduce, so it kind of, you know, really justified the functional programming stuff. But for the context of this, if you take away I can do a map, you'll be good for the second notebook. Right, and this is kind of the motivating example, right? Here we do a star map, but kind of just understanding the syntax of mapping over a, you know, a function and an iterable to reply. So a function to reply to that iterable is kind of where I want to get to. So let's talk a bit about functional. Can I? Probably not. What is functional programming? There's kind of 3 ideas. One is this idea of no side effects, right? Or essentially not depending on or mutating state in the outside world external to your function. Variables that don't vary, this idea of immutable data, right? Not taking data and mutating it, but instead writing it to disk and reading it would be the more functional way to deal with it. The other one is sort of first-class functions that we can pass around and use in Python. Functional programming, I think, one of the big benefits of this is it just encourages good functional decomposition. It just encourages you to write functions, which is almost always a good thing. Right, I kind of leave you guys to read this. A lot of the notes in here I kind of won't go over and talk over. It's kind of extra detail for you guys to read as you want to, but this idea of imperative versus declarative. Functional programming is all about just saying kind of what you want, and often the mechanics of, so for example, if we look at this map here, the mechanics of how this map is done, you know, whether it's done over a cluster or over a process and stuff like that, it doesn't really appear at this stage, right? That kind of complexity is hidden inside that function call. Whereas, you know, imperatives type programming, you have a class and it's very kind of, you're telling the computer exactly how to do it. Whereas here we're more kind of saying, this is what we want, this function, and then this kind of map will take care of where and how to run it. Yeah, no side effects, this not depending on state, not depending on the outside world, kind of becomes this, you know, computer science term of idempotency, which a lot of people say to sound clever. That's what I'm doing here. The idea basically is that when you run a function, it should always run the same way, right? There should never be anything that can happen, you know, in a database or on S3 or, you know, in some other part of the program that will cause that function to run differently, right? Same inputs, same outputs, right? Is really core to this idea of functional programming. So some examples of this. This is kind of a very simple, somewhat trivial example. I just need a little bit more space here. We have a door, right? We want to close that door. One way to do that would be to implement a toggle, right? Which looks at the position of the door and just takes the inverse, right? This way of closing a door is not idempotent, right? The behavior of this toggle or door closing functionality that we want changes each time we run it. The reason it changes each time we run it is because we depend on the state of the door, right? That's essentially not being idempotent and seen as sort of not adhering to these functional programming practices. A way to do this in an idempotent way is essentially just always close the door, right? The concept of fail-safe in engineering. There's a bunch of different kind of ways this stuff comes up. variables don't vary. So this is a bit of an interesting concept because variable itself, suggests something that should change. This idea of variables that don't vary is essentially relying on immutable data as the input and output to your function. So here we have a simple dictionary. It gets passed into a data pipeline here. I just changed the stage to processed. This way of implementing this mutates this raw dictionary, right? And we can see now our raw dictionary has been lost, right? This is an example of not immutable data, right? Instead, the correct way to do this, where we both maintain our raw dictionary data, right? That data doesn't change, is essentially just make a new dictionary, right? Take the data that we want, return that. But again, the key idea here is that this variable raw, it's always raw, right? We never change it. If we do work on it, we will create something new, right? A new variable that will never change. And first-class functions, this is kind of for people that are kind of introduced to programming through Python, like me, kind of take for granted. It's just this ability to kind of throw around functions as if they're variables, to throw functions into other functions. Again, for Python programmers, we kind of take this for granted. There are other programming languages where you can't do this kind of stuff. So just to summarize these three things, these kind of like ideals or goals of functional programming: no side effects, not depending on state, idempotency, this first one. Second, variables that don't vary. My data is always there. Even if I work on it, I can still go back to it. And first-class functions. Any questions at this stage? Cool. Right. So I kind of mentioned that map is like the big motivating idea or function of this whole section, right? You need to take away how to do a map. A map essentially is exactly the same as a for loop functionally, or applying a function to each element of a data frame. I have a data science background, so a lot of these notes will be kind of data leaning. So the first example of using a for loop, which most people will hopefully be familiar with, we just operate on each element of this list, and we call this function on each element. This function just lowers the string, right? Just takes that first capital letter and lowers it. We can achieve this exact same functionality using a map, right? Obviously, we need the function here and the data as well. And this map syntax, the first thing we put in is the function that we want, right? So this lower here, whatever function that we want to apply to each element of this input, right, is our first input. And the second element is just the thing that we're iterating over, right? In this case, just a list of cities. One of the things that's a little bit, is a bit of a gotcha, or you need to learn about a map, is that a map evaluates lazily. It doesn't actually run that for loop when you create this map object. And just calling list on it will just actually run that map computation. It's just kind of an additional, I need to call a list on a map thing, which you need to remember with maps. But by and large, it's roughly the same. It can still easily be a single line, like a list comprehension. Right, so that's map. So really important to understand this, to kind of understand that, okay, it's just a for loop in a different syntax. If you get that, we'll be all good. Right, lambda functions. Lambda functions is another one that kind of becomes important in functional programming, because quite often we just want to dump a function in here very quickly that does something very simple. Like, for example, this is a very simple function. It can easily be a lambda function because just one line. An example of doing this exact same thing we did above with a lambda function, this lambda syntax, just declaring this anonymous function. This is what's going in, and this is what's coming out, right? And one of the things to understand about lambda functions is that we have some flexibility over what we do here and what we do here, right? So I can input a tuple, you can take the sum of that tuple, right? You have complete flexibility of what you do on the input and what you do on the output. I can see some people struggling to see, is this big enough? I'll go one more. Actually, that's maybe too much. So complete flexibility on input and output. You're kind of limited to a single line return. You're obviously doing multiple lines here, as it would be a bit inconvenient. You would just write a normal function. And you can see this kind of returns a function object, right? We could assign this lambda function to a variable, then essentially we've done the same as if I did something like lower equals. Sorry, I use a different keyboard layout at home, so you'll see me struggle to type some things. This is exactly the same functionally, except for the thing's obviously different as doing def, def name, def lower, some function. Okay, filter, right, we're almost at the end of me talking, guys, not too long. Filter, very simple, just kind of doing an if statement, a conditional on each element that we're iterating over. So you kind of get a map for free with a filter. It's kind of doing a map and then an if statement, the same way we can kind of see with this list comprehension. So list comprehension, for city and cities, we just have a conditional that will determine whether we include that thing and what we get back. Exactly the same as what's going on in the filter, right? We have this lambda function defined here, which just does that conditional, right? Just use a lambda function to do it. It's just kind of easier, keeps things on a single line. Population is the thing that we're iterating over. Yeah, you can obviously do the same thing with a for loop. Right, last one. Yeah, I'll do that when I get done. Last one, so we've had map, which is like a for loop. We've had filter, which is like a for loop, with a conditional. Reduce is slightly different. So with a map, you always get the same amount of objects out that you get in. With a filter, you might get the same, but you'll probably get less. With a reduce, depending on how you're doing the aggregation, you might get one, or you might get an object with keys, which we'll see. So if we want to do something like just sum all the population in each city, actually this populations thing, I didn't really talk about that too much. Just a simple list of tuples. First one name, second one just a float. Yeah, apologies if people have gotten lost there. So here I just iterate over this list of tuples. It's actually a name tuple just for convenience. So for each city in these populations, I just pull out the population, I take the sum of it, right? Super simple and easy. Now, understanding kind of how the reduce function works in Python, the one that we'll kind of see down here, it's actually really good to have a mental model of a for loop with some sort of internal state that's being passed on to the next bit of the loop, right? If you kind of think about how you would do a reduce using a for loop, this is maybe how you would do it. The reduce function from isotools, which we look at below, it's the same thing. You kind of pass in this initial state that's going to be passed across each element of the iterable. That state gets mutated as you kind of move across, exactly the same way as the reduce is working. You don't really see that here, right? So this is actually probably a better mental model for thinking about how a reduce works in functional programming. Right, I will need to grab this. So for whatever reason, reduce is not a built-in in Python. It's hidden away in functools. But we can kind of see it's roughly similar to what we had with a map function first, then the thing that we want to iterate over. We just have this additional concept of like an additional value, right? This initial value is the same as total here, right? You can think about it. We kind of need the reduce to give the reduce a place to start, right? An empty dictionary or a zero is usually a natural place to start, but you can kind of change it if you wanted to. Right. So how would we use reduce to do this kind of summing over a list thing, which is quite easy to do in a for loop? So this reduce syntax, reduce function thing we want to iterate over, right? Populations, and then initial value, right? So we have this initialized to 0. This is exactly the same as total. And then using reduce here, two ways. One, using the function, defining a separate function, and this here, I'm just defining using a lambda function to do it, which perhaps would take a bit of time to understand. I'll just go through it super quickly. So lambda function, lambda syntax to define the function. Again, we have some flexibility over input here, right? So I have both my accumulated value of total and my kind of new element in the iterable, which is pop, right? Pop would maybe be better called city here. It's maybe slightly confusing. And then I say, how do you want to do the aggregation? Here I'm just doing a sum, right? So I take the previous value, I increment it, and move on to the next one. Here's what I'm iterating over. Here's the initial value. Right, you can do more complex things. So here I'm actually doing a group by, right? You can see that what I'm passing in as my initial value is no longer just a float, it's actually a dictionary, right? Because these are the aggregations that I want to do. Yeah, definitely things you could change about this code, but roughly it's, it obviously works fine. Cool, right, now your turn. So there's a couple of exercises. I have about 20 minutes for exercises, but I think I might cut that to 10, just for the sake of time, because I'm a little bit further ahead than where I thought I would be. Although actually we started at 20 past, didn't we? Sorry, I think we're good. Cool, so yeah, I'll give you guys about 20 minutes or so, to work through these. There's 3 exercises, I'll just go through them quickly. The answers are already here as well. If I was in this tutorial, I would just go straight here and look at these, right? Don't, feel like there's anything wrong with doing that. Other people like to kind of, give it a go and see if they're clever enough. I kind of know that I'm not. So 3 examples. First exercise, here's some code, right? You can kind of see some of the things we've been doing as, alternatives to functional programming, for loops, if statements, all these kind of things, right? Here we have some aggregation. And here's the result you get. And the idea is to just do this in a functional way, using map, filter, and reduce. You can use all 3 to solve these problems. The second exercise, again, I appreciate you might not get through these. Creating a pipeline. There's no starter code to get going here. Selecting the cities that have populations greater than the average of all cities. So it's a little bit of a nasty or annoying question because you kind of need to know the average before you do that filter, right? There is a way to do it in a single reduce step, which I show in the answers. But one of the things that's really important, I kind of don't write it here, but I should have, is whenever you have a task like this, and maybe you're thinking, oh, I want to do this in a functional programming way, just first write something like this. Use for loops, just do it in the way that you're kind of familiar with, and then take that program and try and make it into a functional program. I think that's a much better way to start out, because kind of understanding where to put a map and where to put a reduce and stuff ahead of time without any code to work is difficult. That's why I've made this question like that, so it is a bit more difficult. But definitely in general, you want to think about first doing it in a way you're comfortable with and then kind of swapping things out. And then, yeah, another sort of group by average population for both continents. Yeah, this is very similar to a MapReduce example. Cool. So yes, what I suggest, maybe we go just until the hour, on the hour. Yeah, is it common to do practical exercise in these tutorials? I kind of thought it would be. It is? Okay, cool, good. Cool. Yeah, and I think if anyone has any questions, if you can just come up and do them up here, because I don't think I can get back to everyone. Although it's quite difficult for people to get out through. And I'll show the repo again. Okay, good, cool. Nice.
Hey, can I just ask? Um, who in here is also looking at venue lists and looking at the online chat? Is there anyone else, like David has the chat window open. Does anyone else have it open? No. Oh, Sam, are you hanging out for the tutorial? The reason I ask is I'm kind of looking for someone to maybe act as an interface between the live room. If there's like questions in the chat, you could maybe relay them up. Then I will not. Yeah, cool. If while your battery's okay, if you can be in the chat with the live stream off. If you turn the live stream off, your battery and the Wi-Fi will be happier. There's
Yep. Uh-huh.
Okay, I'm probably going to be out of it.
Hey. Don't know if okay, here's my mic back. Okay, guys, I'm just going to run through the answers now. I appreciate the exercise of that engaging that everyone's ignoring me now. I'll just run through these super quickly. So the answer to the first question, which is about, summing total population for a continent. We can do this in a single step. So this lambda function here is our sum function, right? Whether you call this a single step or not is, it's maybe 2 steps, because this is, I would say this is 2 steps. The sum function, right? We have this, accumulator variable that we're sort of passing around the iterable, and then this filter, just filtering on a certain continent, Pacific in this case. Okay. Is that me or? Is it? Oh yeah, you can still see it down there as well. All right, I think we're back, guys. Thanks for that. Cool. I'll just run through these answers super quickly. Second one, this is this one, we're calculating the average, right? And when you kind of initially look at it, you think, oh, we need to calculate the average first, right? Which is what we do here. And then do a reduce. And then, calculate the average, sum over the count. You can actually do it in a single step. I won't kind of go and explain this. But you can see we kind of take advantage of, some complexity in the thing that we're iterating over, this kind of initial thing, tracking these two values, and you can kind of calculate the mean as you go that way. Not that important. Lots of people would probably just prefer this for ease of understanding. Right, and then the last one for this notebook was just finding, essentially doing a group by population. Which I think is very similar to one of the examples that we showed. You can see there's some horrible monstrosity here, which attempts to do it in one line. But these are much easier to understand and work with. Cool. Let's move on to the second notebook. So this is kind of the meat of the tutorial. This is the thing that probably will be the most useful to you if you haven't done any multiprocessing or async IO before. Working on a single machine is really nice for a lot of reasons, and you should definitely be trying to distribute compute over your CPU cores, or use the single thread a bit more intelligently with async IO before you think about, I want to spin up 1,000 cores on AWS type stuff, which we'll look at in the last notebook. So we'll kind of talk about some computer science stuff. I'm not a computer scientist, so I have this kind of always try to kind of explain these things for people like me who didn't have that education. We also talk about some basics around how a CPU, what a CPU does, threads and processes. Again, very simple concepts that a lot of people understand, but it's really important to bring everyone along together, especially in an introductory talk. And then we talk about basically these two things. Multiprocessing and async IO. Threading is just kind of something that you shouldn't do. You can just use async IO. And we're kind of solving these two problems, right? CPU-bound problems and IO-bound problems. I'm going to talk a little bit about what those are. So a couple of background concepts that are kind of useful for understanding, how to think about working in, across many machines or many cores. Should you do it, right? There's a couple of concepts that are really useful. One is this idea of horizontal versus vertical scaling, right? Horizontal scaling is scaling wide, right? I take my job and I use many workers to do that job, right? Usually many small workers, right? It's like distributing that way. A second way of kind of scaling is just to get one very big machine, right? And that would be the idea of kind of vertical scaling, right? We're taking this one job, this big job that we have, and we just get one real big thing, and we kind of scale into it, rather than horizontally scaling where we let's get many things and scale wide. Really useful concepts for kind of talking and thinking about distributed computation. The other one that's really useful is fixed versus variable. I didn't draw a picture here. I probably should have, because it communicates really well as a picture. You can basically just think about a line. The slope is the variable cost. The intercept is your fixed cost, right? Any type of more complex things, whether it's multiprocessing, async IO, I guess, has some overhead, but not much. Certainly, if you're thinking about spinning up clusters, you end up hitting a lot of fixed costs, startup times of clusters, run times of clusters, and all these kind of things. Processes and multiprocessing, which is kind of relevant to this section. So this balance between fixed and variable cost is kind of always something you need to consider, right? If it's going to take you 10 minutes to start up a cluster, probably not worth parallelizing something that takes a couple of seconds, right? This kind of logic is really important. And you'll kind of see, especially when you work on your own machine, sometimes you might multi-process something and it's actually slower than just doing it in a for loop, just because of that fixed cost to start up processes and run them. You might also run into memory problems, with multiprocessing, depending on what you're doing. Right. So why distribute computation? One reason is just to do things fast, right? We don't care about CPU time. We care about real-world time. especially nowadays, the last few companies that I've worked at have not been so concerned about cloud costs, but they have been very concerned about developer time. So distributing computation kind of gives you a way to, save some developer time, but, maybe pay a bit more on the cloud or have to do some kind of slightly more complex things. Yep, and these two problems are kind of the focus of what we're going to talk about: CPU bound, IO bound, and here are kind of the two solutions here. And there's kind of two solutions to these problems, two kind of tools that we have to do things quicker. One is to use more hardware, right? We do things in parallel. We use CPU cores that are just sitting unused on our machine, or we do things more intelligently just by waiting, handing off execution and stuff like that. Those are for IO-bound problems. These messages I'll be repeating again and again because they are kind of the core messages of this notebook. Sometimes you want to use more memory, right? It's not necessarily that you want to do something fast, but you might just want to work on a really big data set, right? And that data set kind of needs to be held in memory for some reason. You need to do a calculation across the whole data set. We've kind of seen at the end of the last notebook that even something that intuitively you think that you need to do all at once, like taking an average, you can actually do incrementally. And this is this kind of idea of batching data. Dask data frame does this. We don't talk about Dask data frame, but we do talk about Dask. But these two solutions here are essentially the same as above, either using more hardware or just being a bit more intelligent about how we do things, right? These are kind of these two ways to solve problems. Just throwing more compute at it, or actually just thinking a little bit about what we're doing. Cool. Yeah, and why just on a single machine? I think it's easier. It's really great to not have to rely on anything third party. You'll kind of see when we get to the cluster, the next notebook, I'll show you some of the stuff I was doing last night, trying to get things working. Yeah, so this notebook's great. Things just run, Python standard library, not paying anyone any money for anything, don't have to have an account for anything, don't have to worry about credentials for anything, which we usually just worry about all day. Cool. So hardware and software, this will be, for some people, very basic, but it's worth going on. Here's kind of a mental model of how a computer works. We have multiple processes running on our computer. Your music player, maybe you're doing some stuff in Python, this browser, right, all individual processes. And inside these processes, this is kind of a good mental model. It's not necessarily 100% correct, but I think it's very good. Inside these processes, you have processes a software thing, a thread is a software thing, and it's just kind of like a path of execution, right? If I want to run a process to completion, I just kind of need to think about running all the threads to completion, right? These threads kind of exist in the program. The kind of simplest way, and this is how Python will run, we get one of our CPU cores. You can think about we kind of attach it to a process, or we kind of, okay, this core is running this process, and kind of at the same time, this core is running that thread in that process, right? So one core, one thread, one core, one process. This is how Python works most of the time. There's this thing called the GIL, which I think most people will have heard of. Basically means you can only work on one thread at a time in Python. That's just kind of how it is. It is possible to do other things, right? It's possible to run multiple threads in one process using, multiple cores, right? You'll see that we still have this kind of map between one core runs one thread, and I think that's a useful thing to stick with. I talk a little bit about multi-threading and hyper-threading and stuff, but I think just having a mental model of I have 8 CPU cores, I can run 8 processes, and because it's Python, I can run 8 threads, right? That's kind of where you end up. There are opportunities for multiprocessing in Python. I think I've mostly just said most of this out loud. I'll come back up a little bit. Multi-threading and hyper-threading, you can kind of read through if you want. But I think it's good to kind of stick with, especially when you're writing normal Python, I can't use multiple threads at once. I have one core, I run one thread and one process, and that's kind of where we are. Right, I'll just see if I didn't say anything. Yes, so that we kind of have these two units, these two software concepts, threads and processes. Process kind of wraps around threads. The big difference between these two is, let's say I want to run 2 units of compute. If I can do both threads in one process, that means I don't have to incur a huge amount of fixed costs spinning up another process. Each process has its own space in memory, but if I'm multi-threading, right, doing something like this, these threads are sharing the same memory space. You can see it's kind of separated from, this other process. That's both good and bad. It's good because it means we use less memory, but it's bad because this thread can get in the way of the other thread, right? It's a kind of a, classic trade-off there. Yep, so threads are kind of lightweight, easy, fast, but we can't really do it in Python, not, kind of what we want to do, which is I have one Python process and I have 8 threads running in there. In normal Python, that's hard to do. Processes talking about the memory things. The one kind of exception to this rule is, and it's very common in data world in particular, is using low-level libraries like C or C++ from Python. You're kind of you're able to do these things here, because when you're calling, say, NumPy in C, C is will happily multi-thread. You can multi-thread safely. So we are doing multiprocessing in Python, but not really. Sorry, multi-threading in Python, but not really. That's kind of the one got you that you can kind of do something like this in Python. Right. So that's kind of computer hardware and software stuff. The important things are threads, unit of computation, process, this thing that kind of wraps around threads. These are software things, and then CPU cores. One core runs one thread, at once. And yeah, again, like I've said, usually in Python that means one process, one thread. Right. So we have these ideas of these kind of computer science ideas: concurrency, parallelism, and asynchrony, which I'm going to struggle to say most of the talk. And to kind of explain these things, I have these 3 examples, right? One is growing a tree, the second one is mowing a lawn, and the third one is playing many games of chess at once. And we'll kind of use these examples to explain these, computer science things. So concurrency is this idea of doing, well, not necessarily doing, but managing many things at once, right? So concurrency is like sort of like a parent property to both parallelism and asynchrony. I should have drawn a picture of that. But it's kind of this general idea of I'm not only doing this thing, but I'm doing that thing. I'm not necessarily doing both at the same time, but I'm kind of aware of both of them. I'm managing both of them. That can be doing both at the same time, which is parallelism. Right, I'll kind of, scroll through that. You can kind of read through that at your own time. So we have this idea of concurrency, managing, doing many things at once. Parallelism is a special form or kind of a special type of concurrency, and this is actually doing many things at once, right? So I'm doing this thing at exactly the same point in time, I'm doing something else, right? Usually the same thing on a different input, a different kind of data. So parallelism fundamentally requires many workers, right? You can't do anything in parallel with one CPU core, right? Because that one core runs one thread, right? You're kind of stuck to doing one thing. If we introduce more hardware, additional cores, now I can start to use those cores to run, threads and additional processes because we're in Python, and do many things at exactly the same time. Yep, and you can kind of think about parallelizing at kind of multiple different levels, right? But we'll kind of be sticking to, these 3 in this notebook and the next one. Right, so we have concurrency, this kind of idea of doing, managing many things at once. Parallelism, a special form of concurrency when we're doing many things at exactly the same time. Asynchrony, which might not even be a word, I might have just made that up, is this idea, asynchronous programming doesn't really map exactly to parallelism because it kind of has this programming context, but it's fine. The basic idea is just that when we're waiting for something, right, and the things that we wait for in computers are reading and writing to disk, or waiting for an API call, essentially reading and writing to the network. While we're waiting for that other thing to happen, we can, instead of waiting, just take the CPU and let it do something else. That's all that kind of this asynchronous idea is. So it's not parallelism, because when it can be looked at parallelism. It depends whether you look at that waiting thing as a thing or not, because you're waiting for it, but you're not actually doing anything. So it gives you a form of parallelism where my main thread can keep going, doing something else in Python while I'm waiting for the network, right? Whether you call that parallelism or not, it's kind of up to you. You can see it as both ways. But it's a form of parallelism, but not the same as this kind of parallelism where I'm kind of, it's not just something I'm waiting for, but it's any computation I'm doing in parallel. Yes, but the cool thing about this idea of asynchronous, we get this form of parallelism with a single CPU, right? So we're not throwing more hardware at the problem here. All we're doing is being a little bit more intelligent. We're pointing out these places in our program where, okay, you can wait here, right? You can go do something else while you wait here, sorry, is the way to think about it. Cool, so these three ideas, concurrency, parallelism, asynchrony. So let's think about these three kind of motivating examples, growing a tree, mowing a lawn, and playing many games of chess at once. This first example, growing a tree, you just can't really do it quicker, right? There's no opportunity to do anything in parallel with growing in a tree. There's no opportunity to kind of wait for one part of the tree, you know, and grow the other part of the tree while you're waiting. It's just a tree, right? There are some things you want to do. There's just no opportunity to do anything concurrently, right? And it's important to kind of understand and remember that. A second kind of, our second example is mowing a lawn. So let's imagine I have a lawn, right? And I want to mow it quicker. What I can do is I can get more mowers, essentially throw more hardware at the problem, right? And I can mow those different bits of lawn at the same time in parallel, right? This is, you know, parallelism. This is multiprocessing, right? I'm not being more intelligent about how I mow. I'm just mowing more at the same time. I need more mowers to do it. The final example is this idea of one chess grandmaster playing many games of chess at once, right? How does this kind of relate to what we're talking about? So when our grandmaster gets to, you know, his next game, if we weren't doing this in an asynchronous way, that grandmaster would, let's say the grandmaster takes 2 minutes to decide an action, you know, regular Joe takes 20 minutes. If we're doing this in a synchronous way and an unasynchronous way, our grandmaster decides a move in 2 minutes and then sits there and waits for the other person to make a move for 20 minutes, right? That's a synchronous way to do it. These two things are in sync. And essentially the grandmaster, even though the grandmaster is just waiting, right, his CPU is kind of not doing anything. Because we're in sync in that game, there's no opportunity to do things quicker and we kind of do things slower. Where instead, if we do this in an asynchronous way, while we're waiting for the next move, our chess grandmaster can move on to the next game, take an action there, etc., and he can move the whole way around the board and kind of get back, resync, restart that thread. So we have this kind of idea of handing off execution while we wait and then restarting, right? There's kind of two things there, both being able to hand off and being able to restart. But if we can do that, then essentially we can just, while we're waiting, go do something else, come back, you know, and we kind of save, you know, clock time. Any questions at this stage? Sorry?
Is that Bobby Fischer's name? Do you know?
Yes, it is. Yeah, it is Bobby Fischer. Yeah, I should probably have a caption here. It's a bit, yeah. Yes, this is Hank Hill, by the way. Yeah, I think that was right. Cool. Right, I kind of talked a little bit about this. Should probably be in background a little bit because I've mentioned this CPU-bound, IO-bound heaps. But I think it's a good way to think. The one thing that's been really useful for me to think about computers is just narrowing it down to three things. You do computation, you talk to people, or you remember things, right? That's kind of all computers do for us. These three functionalities can be mapped directly onto problems we have with those functionalities. CPU-bound problems, right? I want to do compute, but you know, all my one CPU is going as hard as it can, right? It's vertically scaling as much as it can, and I'm now bound by that CPU. IO-bound, you know, my thread is sat there waiting for a long network call, right? As an example being IO-bound, IO read-write. Memory problems we don't get into here. I can have a conversation. I have a list of a bunch of ways to solve these problems if you want to ever talk about them. These can actually be quite nasty for some people. But we're really talking about these two things, CPU-bound and IO-bound. Cool. Threading, I'm not going to talk much about this. There's some content here. But basically, the way to think about threading, and when I'm talking about threading here, I'm talking about a specific module in the standard library, right, from, you know, import threading. There's just really no, because of Async IO, which came out in Python 3.4, I think, there's really no space or room for threading in your toolkit, in my opinion, obviously. I wouldn't suggest looking at it. You kind of get the impression with threading that, oh, we can do multi-threading, but you still can't do multi-threading. You're still limited to a single thread, exactly the same as Async IO. So I would kind of really just forget about threading as a thing. There's some links to some talks here. This is a great talk. This guy's a great guy, talking about how to do multi-threading code. He's a very good programmer, and it looks very difficult. So I would suggest just don't worry about it. Threading is kind of, we don't need it. Because we kind of have these three, I think I'll show them, yeah. These three things, threading, multiprocessing, async IO, but we only have two problems, right? IO bound and CPU bound. So we can throw one away. We throw away threading. Yeah, so just something not to worry about. Right, talk a little about C++ thing. Multiprocessing. So because I'm a data person, most of the problems that I have are CPU-bound problems. Multiprocessing is an amazing, fantastic tool that should be in your toolkit. Async IO is worth learning and definitely a valuable part of this course, but you can actually just multiprocess everything if you want to, right? And just have multiple cores, waiting for the network in parallel if you want to. It's totally fine. You just incur the memory overhead of using multiple processors. But multiprocessing is, if you just take away one tool, this is the one tool to take away. I think it's easy to program personally. It just ends up being something like a map, right? This is why, this was the motivating example of why we went through all the functional programming stuff, just so you understand and you're comfortable exactly what's happening in this map call. Here's a function, here's an iterable that I throw into it, right? That's all that's happening. So you can, this is this example of this functional style of programming allow you to not really worry too much about whether you're multiprocessing or just normal map, right? I just write a map, and then I do it in multiprocessing, I do it in normal Python, I can do it on a cluster, right? This kind of hiding away all this detail is one of the reasons why maps are used to do these things. Right, multiprocessing, yeah, for loops and maps, these kind of things. Yes, this is the big thing to remember. Multiprocessing, it's great, but it has a memory, sorry, to remember, it has a memory overhead, which can be a problem. You can also get some problems. Sometimes it's difficult to get standard out coming back into the main process. Yeah, you kind of deal with those problems when you come to it. Right, so let's kind of walk through this code. I appreciate I've gone to the end very quickly. This compute intent task, I think it just creates a random string of so many letters. You see, it's a lot of letters, just so we make it, a CPU-bound problem. So we start out with a for loop, right? Again, as I mentioned, it's very okay to just start out writing a for loop. If that's what you're comfortable with, just write a for loop. Then convert that into a map, right? So this is the map we call list here because that's how things work. I wouldn't pay much attention to these things here. We kind of don't really care at this point. Well, yeah, maybe the average of these two versus this one. But what I'm trying to say is don't think a map is quicker or faster than a for loop. It's basically the same, right? It's functionally the same. You're not saving any speed by just using list map. You are saving speed by doing pool.map. Here I'm creating a multiprocessing over 2 CPU cores, right? And each time that I go, so when I go through this iterable of number of words, 1,000, this is a list with 1,000 like 8 times or something like that. Each time I run this function, I spin up a new process or I use an existing process. It will happen a lot. I run that compute task and I return, right? And it's quicker. It's not kind of exactly twice as quick, but kind of thereabouts. And that's kind of it. There are some kind of nice tools or things that are useful in multiprocessing, like functools.partial, star maps and stuff. But you'll kind of come across that as you need them. The big thing to understand is if you can get a map, then you can just multiprocess without really thinking about anything. Yeah, hopefully for at least some of you, this will be a useful thing, because this is really the, okay, you can do things a bit quicker now on a single machine. Right, so that's how we solve CPU-bound problems. If you want to do a bunch of things, obviously these things need to be, you need to be able to do them in parallel, right? Here we're just creating random words, so I don't need to wait on the last one. If you did, then you can't do things in parallel. This idea of independence, I didn't really stress this that much, is really important when thinking about, can I parallelize a task? Okay, I think we're getting there. Right, Async IO. So as I mentioned, Async IO is kind of a late comer to Python. That's why threading and Async IO, they basically fill the same space of single-threaded computation, single-threaded concurrent computation, or asynchronous computation is the way to think about it. So unlike multiprocessing, I just still use one core, one thread, right? I'm not throwing any more hardware at the problem when I do Async IO. I find it a bit harder to program. Async await keywords are fine, right? The thing that's a little bit hard when you use, do I have any examples of this? Yes, this is a good example. This is the equivalent of request.get in an asynchronous way, right? I'm having to use, actually, yeah, I said we didn't have to use other libraries here. With that Async IO, essentially you need to introduce, because we have to be more intelligent, right? We have to think, we have to write different code. You kind of have to introduce non-blocking versions of everything that you already use, right? So sleep becomes async IO.sleep, right? And all this kind of stuff. So it ends up having this kind of weird effect of both, maybe I can open a script so you guys know what I'm talking about. Both now all my code has async in front, right, which is fine. I mean, it's not that big a deal. I now have to use special kinds of things that I already do. I have to sleep in a certain way. I have to make network requests in a certain way. I have to read and write to the disk in a certain way. This is us being a bit more intelligent. And then some, you actually have to run the program a little bit differently. This kind of isn't too big a deal. You can kind of get used to it. But this is the real annoying one. Having to rely on another library to do this, having to make the decision on what to do. You obviously get a benefit from it. It's not that it's not worth it. But compared with multiprocessing, which is just like, okay, if it's a map, it's already done. Asynchronous program requires a little bit more things to think about. A final challenge that kind of destroys us being able to do these examples in Jupyter is Async IO is already running in a Jupyter notebook. So you have to use a script, which I think I can do here. So that kind of happened reasonably quickly, but essentially what's happening is we have these long-running tasks. These are like our IO-bound tasks. This is me waiting for the network, waiting to read and write from disk. And essentially, these three tasks, instead of running sequentially, they run at the same time, right? So that's why I get 1, 1, 1, 2, 2, 2, right? I don't get 1, 2, 1, 2, 1, 2, right? And this is why the whole thing runs in a single second, right? So all those three sleeps that I did, I kind of did them in parallel, right? On a single thread. And that's kind of the benefit or the use case of Async IO. I don't want to, throw more cores at it. I'm actually just waiting. Let's just be a bit more intelligent and kind of do things this way. Cool. Yeah, so exercises again, I'll kind of run through them super quickly. There are answers to these ones as well. Yeah, I have to think a little bit about how long to do this. Maybe 20 minutes as well, I think. And the examples are, there's some CPU-bound code in here. It's just I just tried to think of some things that will take CPU a reasonably long time. And the task is just to take this and multiprocess it. You can see there's kind of this nesting of loops. I'm actually not sure what the best way is to do that, whether they should be nested or not, or you can kind of flatten them out into a single thing and run in parallel. Yeah, I'll kind of let you guys take a go out of it as you want. And then the last one is IO-bound problem, which is just downloading some high-resolution images from the internet. You can see here I use request.get, right? Because we're doing this in an asynchronous way, we need to think about replacing this, right, with a non-blocking, right, get, because this get blocks at the moment, right? The thread sits here and waits for the request to come back, whereas what we want to do is essentially do this asynchronously, send out the network request, and just go do something else while we're waiting. This is this asynchronous programming. Yeah, and then I think the final example is kind of the motivating example for the next section. So the exercise is to use both multiprocessing and or async IO, kind of as you like, on kind of a completely malformed problem where things are kind of, there's a whole bunch of stuff happening. This example is the one we will take through into the next section, which is running stuff on many machines and on a cluster and stuff like that. Cool. So I think I can give you guys till maybe 5:02 or so, I think is good. Yes, true, yes. So what I would suggest, if you want to make these problems a little bit easier, just delete a bunch of these, it's fine. If you find it's taking a while. And vice versa, if things are running too quickly, if you're finding that multiprocessing actually isn't worth it because it just runs quicker without it, you can just kind of do more things in your multiprocess, essentially. Yeah. So this idea of fixed versus variable cost. You might not be quite hessing the trade-off as possible. That's kind of why there's lots of downloads here. Any other questions? Cool. But yeah, I think just to summarize the whole lecture, it's CPU-bound problem, multiprocessing, IO-bound problem, async IO, and that's it. If you take that away, I think you've got it. Going. Nice. Spot on, Navy guy. What I'll do is I'll just run through 2 of the answers. There are notebooks, which is weird. Yeah, just run through 2 of the answers, just so everyone's on the same page. This CPU-bound problem we had, which was kind of ended up being these multiple for loops. Oh, actually, no, sorry, it's... apologies for the structure of this code. Yeah, so this is our CPU-bound problem. You know, we have a bunch of images. We want to do some stuff on here. We do things on each channel of the image. That's just to make it slower. You could obviously vectorize that. Yeah, so if I was to think about kind of rewriting this to use multiprocessing, this is kind of what I did. I kind of made a big long list of all the images in the integer channels and then just multiprocess across that. You kind of have to do 2 loops, right? You loop here and then you loop here, but I kind of figured that this probably isn't that hard to do. You know, it's just making a list, but you know, a list of tuples. And you still kind of get the ability to, you know, parallelize across that really difficult bit. Yep, and then the IO bound problem, which is just waiting for all these images. I bet no one got any of these because they're big images. The naive way to do it, you know, I just look over the images. You know, I do a synchronous request, you know, to get the data and then just write it to disk. If you wanted to do this asynchronously, you can see you end up having to do quite a bit of stuff, right? So we have to introduce this async IO.run, right? We have to run the code differently. We have to define, well, I think we make 2 methods. Yes, so this is kind of like my main method. You see that it's just called main in other, I think in the other async example. And here I just gather, you know, all the things that I want to do, right? So you can see already we're having to do a bunch of stuff, right? That's kind of annoying. You know, we have to define multiple functions here, you know, when we just had kind of 1 before. And I've also had to introduce this HTTPX to do an asynchronous request rather than a synchronous request, which I did with request.for. Yeah. So that's how you would kind of change that. It does run quicker too. The problem is it's just difficult to run anything. So now we can move on to the last notebook, which I think for some of you will be the interesting one. For me, it's the difficult one. And just to kind of give you guys an understanding of some of the challenges that I had last night with this, when this loads up, if it does. Cool, so 3rd notebook, final notebook. I want to give you guys kind of a brief overview of other ways to do this in 2022. There's a bunch of ways to do it. One of the reasons is that distributed compute is a very general thing, and lots of things can be looked at as distributed compute. So yeah, I'm just going to talk about some of kind of my opinions or, you know, understanding of some of the things that people use. And then we'll look at a very specific stack of 4 things, which isn't great. 3 of them require an account. So I don't know whether anyone else will be able to get this working. I'm happy to help people, you know, understand how to get stuff working. If you want to sit here and do it, totally fine. Also happy to, you know, have a chat afterwards about things. But this is just one way to do things, and it's kind of an easy way to do things too. So why distribute compute over many machines? Fundamentally, there's only so much you can do on a single machine, right? And essentially what we're saying there is there's a limited ability to vertically scale, right? The largest instance you can get on AWS, you can't get bigger than it, right? So if you're kind of pushing up against the limit of either a CPU-bound thing, or you need more memory on a single job at once, right? You are fundamentally limited there. Whereas if you can distribute compute over many machines, then you can use many, many small machines, right? This is horizontal scaling. Can also be cheaper, maybe. And you get this fault tolerance, because essentially most of the distributed compute things that we'll talk about already have to deal with, okay, one worker dies, right? So you kind of get nice fault tolerance for free, whereas if you're just running one big EC2 instance and it, fails, it kind of, you would need to engineer that fault tolerance in yourself. So you kind of get a bit more resilience. You should hopefully get more resilience with a cluster. Right, so ecosystems for doing this. Historically, Spark has kind of been the way to go. Spark is written in Scala. You can access it with Python, PySpark. Lots of data scientists are using Databricks to do this now. AWS Glue, I think, is also running Spark, or something Spark-like. Yeah, a lot of people don't like Spark. I don't like it personally because I don't really know Scala. I don't want to deal with Java. And yeah, all the times I've had with Spark have not been particularly fun. Ray and Dask are kind of more Python focused. Ray is written in C++ technically, but very much feels like a Python library. Dask, I don't know if it's written in Python. At some point, you have to kind of let go of Python. It kind of depends on where. But Ray and Dask are kind of two ways to do the same thing. You can kind of create these DAGs. You're essentially creating DAGs, direct acyclic graphs, which I actually don't talk about. But these are kind of two ways to do it. They kind of do roughly the same thing. Ray, I think, will run on Dask as well. So they have a good relationship. You can kind of have a look at the two. I went with Dask just because Dask plays nice with Coiled and Prefect. But Ray is a fine tool as well. Ray's kind of differentiation is it kind of introduced this idea, I don't know, introduced it, but really emphasizes, say, actors or stateful distributed compute, whereas Dask is kind of more functional, just running functions. But there is actually ways to do state in Dask. TensorFlow and PyTorch, you can look at, obviously a GPU is massively parallel already. TensorFlow and PyTorch will do multi-GPU stuff. I'm sure it's pretty hard. Fundamentally there you're running C++, again, Python bindings. And then there's probably a bunch of other things, heaps of things I don't know about. Just running lots of lambdas in parallel as, you're distributing compute that way. A bunch of different ways to do things. The stack that I'm going to try to demonstrate here, we'll kind of see how it goes, is Dask, Coiled, Prefect, and EC2. And I'll kind of introduce what these things are. So Dask is kind of like the core execution framework, right? So Dask you obviously have to write your program in a certain way. We're not going to write any Dask, we're just going to write Prefect, and Dask will get Dask for free. But low-level Dask code is not something I've written, and not something I would. Ideally, you're using Dask, but you're not having to write Dask. Is kind of what I'm trying to do here. So it's a fundamental part of the stack, but we will never ever talk about any of this stuff, right? It's all kind of hidden inside the way we're using Dask with Prefect. But the way to think about Dask is it's kind of like the core of the stack. It's responsible for creating the graph, executing the graph, managing the cluster, and all these kind of things. But we will never really see it that much. Coiled is essentially only exists because AWS is hard. So all that Coiled, well, not all that Coiled does for us, essentially takes your AWS account and will set it up to be able to run Dask clusters. So all the AWS permission stuff, internet gateways, VPCs, it'll build a Docker image for you from your requirements file and stuff like that. It really tries to take away all of the sort of YAML hacking, CloudFormation-y type stuff that you need to do a lot of to get most things to work on AWS. We could not use Coiled. You can, essentially build everything from scratch yourself in AWS. In my experience, that takes around a week or two. So whether you want to go through that week or whether you want to introduce a dependency on a third-party tool and account is kind of up to you, right? But we're using it here just because it makes things a lot easier. But essentially, it's just doing infrastructure management for us. That's all, right? If AWS didn't exist, Coiled wouldn't exist, right? It's very kind of tied. It does GCP as well, Google's thing. Prefect. So Prefect is an interesting tool. It's kind of it's kind of bread and butter, I would say, is batch ETL, kind of classic data engineering work. It's a data orchestration, workflow management, pipeline tool. Scheduling, monitoring, all this kind of stuff is kind of what it does well. I'll give you a look at kind of some of the scheduling and the monitoring, but you don't really, we won't be using that at all. Essentially, we're just kind of using Prefect as a wrapper around Dask, and I'll show you that now, what's happening. So, I will try to run this on a cluster and just kind of see what happens. Prefect. Where is my underscore? We'll just kind of let that sit in the background and see. I've been trying to run things when we've been here and getting some errors I haven't seen before. I'm also struggling to sign into pretty much everything. So that in the background is just, please sign in. One thing that's really interesting, I can't get access to EC2 at all here, which is a little bit worrying. So if the cluster kind of stays around, I won't know about it. Let's start out. I'll find out when I get home. I'm going to go through all the stuff. Maybe I should have gone through it. Did I delete a cell? Yeah. I think I deleted a cell. Hold on. Sorry, I just lost some stuff that I should have. 2 minutes ago, Coiled. Here we go. I think I deleted this somehow. And this is actually run, which is good. Okay, I'm not going to run these again. I'm just going to show you the results and the code. So we're introducing a bunch of tools here. It is a bit difficult to kind of understand everything that's happening. I usually wouldn't teach a tool this way. You try to introduce things slowly and blah, 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 but we don't really have the time. Okay, this script here, source.naive, right? I'm just running it from the notebook, but essentially I'm just running a shell command here. This is the naive way to do the task that we want to do. This is the task from the end of the last exercise, right? I have some URLs that I want to get data from. It's a big zip file of electricity prices. So I go and download that URL, I save it to disk, and then in my next step, I read up that data and I do some work on it, right? Sort of very generic data pipeline. I get some raw data and I do some work on it and stuff like that. All right, so that's a naive way to do it. This is just normal Python. It takes about 15 seconds. If we look at, let's convert this code to, what is it called? Naive Dask Prefect. To just use Prefect and Dask, right? So we're not using Coiled, we're not using AWS, we're still just running on a local machine, right? We're essentially setting up a Dask cluster on our local machine. And to kind of do this, we need to introduce Prefect, and we need to introduce this Dask task runner. This is as much Dask as you'll see, right? We'll show a little bit more detail when we actually show the cluster, but basically this is you using Dask. The majority of the work that you have to do as a programmer here is introducing Prefect. And essentially Prefect, we have this idea of flow, which is kind of like the global job. There's one flow with many tasks. So I have a flow here, I have a task here, and I have a task here. So my previous program is now 2 separate tasks. It now lives in a single flow. This is just in main. There's some slight difference to kind of how we run things. We need to do .submit rather than .run. But by and large, the way that I kind of see this at least is you take your main flow, your main function, that becomes your flow, and any kind of sub-functions that you're calling just become Prefect tasks, right? Hopefully that makes sense. I appreciate this is a lot to introduce, and I've kind of only just started. But essentially all that we've done there is just introduce Prefect. Okay, let's run it on a Dask cluster. And I think we do get, don't know if we get any performance improvement. 15 seconds, essentially no performance improvement. We can then, if we want to stick with Prefect on a single machine, start to introduce some asynchronous stuff, right? So the asynchronous stuff I think you need to introduce specifically. In terms of parallelism, my expectation and understanding and experience with Dask is that it'll find that parallelism naturally, right? So hopefully I'll be able to show you some stuff running you can kind of see. But we kind of need to engineer in the asynchronous stuff, especially inside the function. But you can think about at this level, right, when we're kind of telling Dask and Prefect this is like a thing in the graph, right, it can actually find parallelism around these kind of things, which is really cool. Right, so that's kind of all running on a single machine. I think this one does run quicker, but I'm kind of not too worried about that. The main thing I'm kind of trying to introduce here is just this idea of Prefect and Dask. So now we're running Prefect and Dask on one machine, and that's great. Let me now try to run it on a cluster. I think we started one before, didn't we? Okay, this one actually ran, which is good. Okay, so let me go through the script first. So that's running Prefect and Dask on a single machine, right? That's great. You can do that. It'll save you some time. You can do things asynchronously. You can maybe do monitoring through Prefect and stuff. But the real thing that we want to do here, we're still working on a single machine then. Let's try to distribute compute across many machines. I apologize for these. This is literally stuff I was doing last night, and I just haven't cleaned it up. A lot of these things aren't needed. But now that we're working on a remote cluster, we kind of need to introduce Coiled, right? Remember, Coiled is doing this kind of management of AWS infrastructure for us, rather than just running on our machine. So I've logged into Coiled at this stage, right? You can see in there's a lot more detail in these notes about how to kind of get things set up. But I've essentially logged in and authed with Coiled here. And if you notice when we ran our Dask cluster locally just with Prefect, we essentially said use this Dask task runner. We're saying, hey, Prefect, use Dask. When we go and run on the cluster, we use something very similar, except now we kind of say just go run on Coiled, right? So Coiled and Dask here are kind of reasonably tightly integrated, or at least integrated. And this is still set in the cluster. So we can have a look at that script that I'm running is starting a cluster. This is Coiled, by the way. So here, 8 workers. You guys won't be able to see this. 8 workers. So Dask has a scheduler and then a bunch of workers. So these are all instances on AWS, right? T3 mediums that are running the compute. This is the long kind of startup time of the cluster, blah, blah, blah. Unfortunately, I can't show you the instances here, which is kind of the sort of proof that things are working. We can see, if I get access to it, you can get access to the Dask itself. Kind of has a UI that will show you what's going on, what CPUs are doing. This might not connect. This has kind of been a little bit, okay, here we go. It's also possible it connects after the thing is done, which looks like it's happened. So here are 8 workers, right? 8 CPU cores. These tasks here, so download, if you remember, is this one here. Right, we have 4 URLs, so we kind of do that 4 times. Yeah, and then process 4. So this is kind of already run and worked, which is good, to be honest. Right. Sorry, I'm getting lost. And that's kind of it. I mean, that is now our code running on a separate machine. I'll kind of go through the code in a second. What do we have to do to get this to work, right? Coiled account, AWS account. You don't need a Prefect account technically to do this. We have to set up the Coiled and stuff, the Coiled cluster and stuff like this, and introduce Prefect, and then you're kind of done. And whether you kind of think that's easy or not is kind of up to you. Yeah, that's roughly the stack. I think there's another example I can run, which I think is just an example, but it kind of largely looks the same. Unfortunately, because you can't see the instances on EC2, it's yeah, that's the thing that's I think I have a picture of it. Yeah, essentially you'll see something like this. Your scheduler worker and then just a bunch of instances, running in parallel on side, running your compute, doing whatever it can on your Prefect program. And I think, yeah, there's a bunch of stuff here about how to kind of do things and how to run through all the accounts and stuff. The last thing that I will show just quickly, if it, maybe not. If you have Prefect and Prefect Cloud on top of this, and obviously logged in all these things, then you can see some good understanding of, it's working. Okay, so now you guys can see what I was doing last night. To get this kind of visibility, or this kind of visibility of these jobs. So obviously I've been kicking off jobs just running a script here, right? Because I have a Prefect account and I've logged in using the shell, just like Prefect login or whatever it is, I'm getting some visibility of what's been happening. So I'll show you guys my day yesterday. This was my day yesterday. Yeah, it goes a little bit later. Where was my success? Somewhere here. Yeah, yesterday was tough. But this is kind of not necessary, right? This is just kind of an additional layer of visibility, and you can look at the things and kind of see what's been happening. Yeah, here I'm just downloading 2 URLs, so I process, download, download, process, all these kind of things. Yeah. One thing to point out about Prefect is that this is Prefect 2. They've introduced this new kind of way to look at the task, which I just don't understand at all. Yeah, it used to be much better. But anyway, that's kind of the stack, right? Compute running on EC2. We're using Coiled to kind of set up and manage the cluster, right? We need an account and all these kind of things. Once we have that, we can then use something like this, right? We have to be logged in and auth to Coiled. And then just kind of using Prefect almost here as just like a convenience to let us run Dask, and that's it, And that's kind of the stack. And I don't really have anything else to say, and time's just about up too. So any questions or anything? I appreciate that might have been a bit sort of chaotic. It certainly felt like that to me. Yeah, I think that the key message is just, if you want to do this from scratch, and you don't want to fool around with AWS too much, Coiled will help you out a lot. And yeah, Prefect's a good way to get access to Dask, I think. Cool.
Awesome. Do we have any other questions in the theater? I'll repeat your question once you say it.
What is the best way to write a unit test for this?
Yeah, testing. What is a good way to write a unit test?
For the infrastructure?
Your call.
Well, I mean, I guess something like this. Where do I have one with this one here? I mean, this could be unit tested, I think. This is almost like business logic-y, right? But like, and I guess you can test the download. But if you're talking about, those obviously unit tests. If you're talking about testing, is Prefect running? Can I spin up a cluster and stuff like that? It becomes more monitoring, I think. Like what do you have running automatically to try to get stuff to work? I don't know if you can really unit test that too much. Because the problem is if you have integration or system tests, they just take ages to run, spin up clusters and stuff. Yeah. Does that answer your question?
Yep.
How do you think concurrent features versus let's say the different concurrent?
I'm actually not familiar with it.
So the question is, how would you compare this with concurrent futures?
Yeah, I'm actually not familiar with it. What is it?
Well, it's just like a different library.
Third party or?
No, it's in the standard library. Yeah.
Oh, really? Okay. Yeah, I haven't heard of it, eh? Yeah, I'll have a look.
What was that, Nick? Hang on, I'll pass you the microphone because Nick will probably know the answers to these questions.
I actually filed a bug against the CPython docs during this tutorial. We do not cross-promote concurrent.futures from the threading or multiprocessing docs at all. So yeah, I'll look at that this weekend.
So the recommendation is don't cross the streams.
Basically, most things that people are doing with multiprocessing or threading, they're almost always going to have an easier time if they use concurrent.futures instead.
Cool.
Yeah, so Nick is saying that for most of that sort of threading stuff, you're much better off going with concurrent.
Multiprocessing.tool.map, it's almost the same between the two. But if you're ever doing stuff with threading, then you want to use
You two should chat.
Yeah, well, I just said not to do it, eh? So, yeah.
Any other questions? This tutorial will remain online, won't it? So like, because I had to duck
The
out earlier, I
notes?
can kind of,
Yeah, of
sort of
course,
go through
yeah.
that myself. Yeah, cool.
Yeah, sure. Yeah. Yeah, like I say, I'm happy to give people a hand. Feel free to reach out and email and stuff like that. Yeah, and this last section, I appreciate it's chaotic and people are probably like, what's Dask and Prefect and stuff, but yeah, that's all we can do in this time.
Cool. Thank you very much. Everyone